So you're estimating some unknown parameters. What is better? Is it better to be unbiased or is it better to be biased? Or does it depend? What did people say? Haha. Some people said it's better to be unbiased. Only one person said it's better to be biased. 11 people said it depends. In statistics or data science, basically the answer is always it depends. So if you said it depends, you got it right. But the key thing that is very weird is it's not always better to be unbiased. So it depends. Sometimes it's better to be unbiased. Sometimes it's better to be biased. And I think this is, to me, this is very counterintuitive. How on earth could it be better to be biased? Bias seems bad. So what do you mean? You're telling me that sometimes it's better to be biased? Yeah, that's what I'm telling you. Let's write some of this down. And let me open up. A new note. So this is the surprising conclusion. Sometimes it's better to be biased. Okay, and we're going to see exactly when this happens. And it turns out it's better to be biased only in a particular way. There's one way you can be biased, and that's always bad. And then there's another way you can be biased that is sometimes good. Another thing you got to also watch out for is what does biased mean? So I don't mean biased. Again, this is not the on-the-street word biased. We've had a few of these weird words that mean something very specific in math and statistics and mean something slightly different in real life. Things like significant. In real life, significant means a lot. Right? Did I eat a significant amount of turkey at Thanksgiving? That means did I eat a lot of turkey? But in statistics, it means a very specific other meaning, which is it unlikely to happen due to chance? And they're kind of related. Like if it's a really big effect, it should be significant statistically, but they're not exactly the same. And it's the same thing with biased. So what does biased mean? Biased. It has a specific meaning. So this is not regular biased. This is the special stats keyword. Stats keyword. Keyword biased. And what does biased mean? Biased. Well, biased is hard to define, but unbiased is easy to define. Unbiased means, on average, it's correct. On average, it's exactly correct. Exactly correct. So the thing you are estimating, the expected value of the thing you are estimating, that's the x hat, right? If the thing you're estimating is called x, then x hat means I'm estimating x using the data I have. The thing we are estimating, that has to be the true thing. The true thing. This is our estimate given data. Okay, and a good example actually is the mean. Why don't I use that as my example instead of x? Let's make mu hat versus mu. Mu hat versus mu. The true thing, the true average. The true average. And this would be some kind of estimate given the data of the average. Our estimate given the data of the average. Okay, so that would be unbiased. And biased means they're not equal. They're not equal. Unbiased means this equals this. On average, you get it exactly right. And biased means that is not the case. Now, how on earth is it possible that being, the statement I said at the beginning, sometimes it's better to be biased? How on earth? Like, this seems great. Why would you want this? And the key insight is equal on average. So this is biased or unbiased, which is equal on average. Equal on average. This is somehow incompatible. This does not go with the thing we are doing in this course, which is minimizing error. Minimizing error, right? So equal on average. This is smallest possible error. And that is the reason, that is like fundamentally the thing that is going on here that is confusing, is unbiased is about did you get it right on average? On average, did you get it right? And the error is not about did you get it exactly right, but it's like how big is the error on average. And we saw the main way we're doing this is the mean squared error. So this would be something like the expected value of mu hat minus mu all squared. So compare this to expected value of mu hat minus mu, right? So this is the difference. The mean squared error is the difference squared, and even if you're not right on average, maybe this is smaller if you're not right on average. Okay. Let's see. Should we do more theory? Let's jump into an example quickly first, and we're going to see how this is. So I have a very simple example, the world's simplest example of a mu hat and a mu, where you can kind of see this in action. And as always, I like to start with the world's simplest example and work our way up. So we're going to start with the world's simplest example, and then we'll see it in real life. But I kind of see a lot of the point of this class is to kind of give you these like simple examples and the simple theory that to build your intuition so that when you go into real life data sets, you have something to think about and somewhere to start. It's very easy to pick up like complicated methods, some crazy method on the internet. It's like, people have a nice tutorial, but they won't have the simplest possible thing because I think people think it's too boring. But I don't think it's too boring. I think it's pretty exciting. Okay, let's see my dumb example. Where's my dumb example? This one. Okay, here it is. So let's open it in Colab and bring it in. Okay, and I will zoom in a bit. Okay, so here, very, very simple thing. I have n data points, which are independently drawn from a Gaussian with mean mu secret. That's the true value of mu. And I wrote secret to emphasize that in real life you do not know this, right? You are trying to estimate the value of mu secret, and you want to estimate this secret mean vector. How are you going to estimate this secret mean vector? You run n samples of this game, and you store it into a single array x. X has n samples by n data by n variables. And the key thing is this is a multivariable Gaussian. Okay. This is, okay, yeah, very good. Okay. So n data, n samples, and n vars. N vars here is 10. So mu secret is the vector 3, 0, negative 4, 0, 0, 0, 0, 0, 0. So this is a vector in R10. So our example, estimating a Gaussian mean in 10 dimensions. Okay, so this 10 dimensions part is a little bit new. When we did mean squared error, we were talking about just one number. You're estimating one number. Now we have 10 dimensions, so we're going to have to figure out how we do that, but you'll see what it is. So estimating a Gaussian 10 dimensions, and in my particular example, mu secret, the true answer that we were trying to get to, what did I say, was 3, 0, negative 4, 0, 0, 0, 0, 0. Okay, and there's 7 zeros over there. That's what we would like. So we want to be able to input a bunch of data and output this mu secret. Okay. And we have a bunch of samples. So samples, each xi is mean. Whoa, that n went really off the rails. N, and it's mean mu secret, and it has some kind of variance. And I think I assume that the variance was the identity matrix. So in other words, the components are independent and normal. So normal distribution. And the first component is mean 3, the second component is mean 0, the third component is mean negative 4, and then all the other components are mean 0 as well. So that's what we got. Okay, so let me add some vector signs here so we can remember what's a vector and what's not. That's a vector, that's a vector, that's a vector. There we go. Okay. We have this thing. Okay, let's go back to our thing. Okay. Here's my secret data. Just like I said, it's np.random.randn. That stands for random normal. And I'm getting number of samples and the number of data points and the number of variables plus the mu secret. So this is the mean 0 thing, and this is the mu secret. Maybe I can say maybe something that's a little bit unclear. In real life, you only get one batch of data. You get some number of data points. But to figure out what is working well or not, I'm going to have to repeat the experiment n samples times. So in real life, you only have one data set, right? You download your one data set and that's it. You got to make your best possible choices using the one data set. So in real life, you would have just n data times n vars, the number of data points times the number of variables. But in this practice notebook, I'm repeating the experiment 10,000 times or something. So I'm saying, what would happen if you did it over and over and over again? And by doing it over and over and over again, we're going to see what works better or what works worse. OK, so x is this vector. OK, and this is the simplest possible thing, what I call unbiased estimation. You estimate using the empirical mean. So you just average up your data set, and then you say, that's my guess. OK? So this is the simplest possible thing. Average up the data set. This is the what I call unbiased estimation. Of course, there maybe there's other ways to be unbiased. Let's see. This is the simple unbiased estimation. Average up each component. Okay, so for the first component, here let me change my notation so that I put the sample up here with an I, sample number I, and I'll do a superscript, and then that will save our subscripts to be used for the components. So for example, mu1 will be the average 1 over the number of data points, and I will sum over my data points. I equals 1 to n data. And then I will do x1i. OK, wait. OK, now I'm being silly. OK, this is an x1i. The whole point was that I have these. OK, so I'm averaging these things. And then mu2 will be the same thing with x2i. I'm putting ... here to skip some work, and so on, all the way down to mu10. And these are all my estimates. Hat. And same thing, estimating the 10th component. OK, so you have to estimate the components individually. And you hope that this is close to, we cross our fingers and hope that this is close to 3, 0, 4, ... all the way 0, right? This is the true vector of mu. OK, that's the game. Simple unbiased estimation. You average them up. OK, let's see what is cooking. OK, so here we go. Mu hats is the mean. If you say numpy.mean of the x, and you tell it, please do the average across the data, that's axis equals 1, then I can calculate the mean squared error. And the mean squared error, I can calculate it across my samples. So this is the nice thing about doing it this way. And it tells me the average mean squared error was 0.249. And I can have these nice little plots that tell me what's going on. So this is variable 0, estimating mu hat 0. OK, I guess you got to watch out here, because here I wrote it with a 1, but Python starts at 0. So it's called 0 over there. Let's move these things out of my way. So slight mismatch between the paper and the Python, but that's OK. OK, and that was the one that was supposed to be 3. The true answer is 3. If we get exactly 3, we'd be so happy. Let's see, did we get exactly 3? What did we get? Hey, look at that. So this is 1.5, 2.5. 3 is right in the middle. And look, it's a nice distribution, right? We got 10,000 samples or whatever of this thing. Actually, what was n samples? Let's get the number right. So n samples was 10 to the 4, 10,000. But we only have 4 data points. So we get 4 points. We average together the 4 numbers. I could write that out. So this is x11 plus x12 plus x13 plus x14. There's only 4 numbers that we average together, and we hope and pray that we get 3 as the output. Okay, and do we get 3? Well, sometimes we get a little bit more than 3, right? Let's make it fit. Sometimes we got a little bit more than 3. Sometimes we got a little bit less than 3. And on average, we got exactly 3. That's great. Really nice. What about variable 1? Well, the true average was 0. So this one, same kind of shape. Sometimes a little bit positive, sometimes a little bit negative. But on average, we got it right. OK. Here's variable 2. -4 here, right? So sometimes a little bit more than -4, sometimes a little bit less than -4. But on average, it's correct. So this is unbiased and we can tell unbiased. There's more. It goes all the way up to 10, but I stopped after the first few. Unbiased because why is it unbiased? The average, on average, the thing we're estimating, let's do, for example, the first component equals 3, which is mu 1. So it's unbiased. Okay, I called this the simple unbiased. Here's the first question for you. Question. Are there other unbiased estimators? Are there other unbiased estimators? Okay, so can you think of another estimator that is also unbiased, other than doing exactly what I just did here of averaging them all together? Is there such a thing? Yes or no? This is a great, let's stop here for a mathematized question. So you will say, yes, there are, or no, there aren't. Mathematized. I'm gonna open up a sec. Talk to your neighbors and think while I get the mathematized ready. This is a nice question. Okay. Okay, it is live on Mathematize. Tell me what you think. Can you think of another one or not? Okay, I think almost everybody has answered. I guess let's let it go for another 10 seconds. Okay, let's see what you said. Reveal. Ha! Everyone knows there are. Very good. There are lots of other unbiased estimators. Can someone tell me, someone who selected yes, this is the correct answer. I might have put the answer in wrong, but the answer is yes. Let's see, did I get it right? Yeah, okay, great. Yes, there are other ones. What are they? Someone tell me one. Where's the blackboard? Here it is, okay. Yes. Anyone have an example? What's a different unbiased estimator we could use? The median. Okay, great. The median. That's very nice. The median of x1, x2, x3, x4. All right, I will tell you, the median, if you know the distributions are Gaussian, the median is unbiased. For other distributions, the median will be biased. So the median, I would say sometimes unbiased, sometimes not. Sometimes unbiased. And sometimes not. And sometimes not. So you got to be careful with that. In this case, it is. Anyone have a different one? The mode? The mode. Yeah, the mode. Okay, the mode is interesting. The mode of x1, x2, x3, x4. This will actually not work. So you have 4 data points. Like if I give you 4 samples, what are the 4 samples? They're going to be like negative 0.5, 3, 2, 8, 7, 1, 2, and then 0.6431, 1.237, and 0.0023, right? You're going to get some 4 numbers, and they're going to be 4 different numbers, and you're going to be like, take the mode. They're all different numbers. So the mode could potentially work only if you have a large sample size and you also have like discrete random variables or bins or something. So the mode usually, I would say, doesn't actually work. You can do the mode of the distribution, but the mode of the data in a lot of situations that we care about is not very helpful for the kinds of things we want to do. And most importantly, the mode is very often not unbiased. So usually biased. Also very often biased. So even if you could do it, it could be biased. So I would stay away from the mode. Does anyone have something even dumber than median or mode? These are all very, very smart. I want the dumb answer. We can analyze the dumb answer. Here's the, so okay, we wrote down the mean of x1, x2, x3, x4, which is x1 plus x2 plus x3 plus x4. Oh, I did the bad notation again, right? Okay, I meant to say put them with superscripts. Right? I'm saying I have 4 samples. They're all of the one thing. Okay, you guys know what I'm talking about. It's fine. Okay, average the 4 samples. I used a different notation earlier. Hopefully you're not confused. Earlier I did it like this, right? I was saying the first component, the first sample, the second sample, the third sample, the fourth sample. Now I'm just using the subscripts again. Hopefully it's not confusing. But okay, I want something I call the dumb mean. This is like the mean if you want to be silly and not be as good. But I think this will help us figure it out. Here is what I call the dumb mean of x1, x2, x3, x4. It's like this. You do x1 times a third plus x2 times a third plus x3 times a third plus 0. So you take x4 and you throw it away. You bring x4 over, you drop it on the floor, and you say, forget about x4. We don't like x4. We like only x1, x2, x3. x1 plus x2 plus x3 divided by 3 plus 0 times x4. Okay. This is what I call the dumb mean. That was the mean. I claim the dumb mean is also unbiased. So this is let's call this mu hat for the dumb mean. The expected value of mu hat dumb mean is equal to the true mean. So it's unbiased. This one is definitely unbiased. Beautiful. Probably all of you realize the dumb mean is dumb. It is not as good as the regular mean. But why? How would you explain to somebody why this is not a good idea? This is worse than this. But why is it worse? How would you explain to somebody why it's worse? Is it worse? And why? Is it worse? Okay, I'll spoil the answer. Yes, it's worse. Yes. But why? This is the interesting thing. Right? And this is the kind of analysis we're going to have to do. In a minute, we're going to talk about biased estimators, and I'm going to try to tell you, I'm going to try to explain why the biased estimators are better. But if we can't even understand which of these two is better, then it's going to be really hard to talk about biased estimators being better or worse. So of these two, the mean and the dumb mean, the mean is better, but how would you explain to somebody why is the mean better? How would you measure why it's better? Or how would you figure it out? Is the question clear? Yeah. We don't have the whole population. Yeah. Why is that worse? Here, and let me make another one. This is called the lucky mean. The lucky mean. So everybody knows the number 3 is lucky. So what you do, you take x1, x2, x3, x4, you just output x3. And you see, because x3 is lucky, that will do better than the other ones, right? So this one was also missing 1, 2, and 4. But we need a way to explain to somebody that this is worse. Why is this worse? Why should we not do this one? This is like a super, or you could do like half lucky. Let's do partially lucky. Partially lucky mean. You're like, okay, everybody knows the number 3 is lucky, but let's not go crazy here. Let's do a sixth of x1, x2, x4, and then we'll do a half of x3. So we're doing like 50% of an x3 and a sixth of x1, x2, x4. And this also, all of these are unbiased. These are all unbiased estimators, which is, we're saying is a nice thing. But out of all of these, nobody ever talks about these ones because they're very silly. And of course, the mean is somehow the best one. But why? Why is the mean the best one? Yeah.
The size of x4, right?
The size of x4.
Yeah.
Okay, tell me more. Yes.
The mean could shift depending on the size of x.
Yeah, but look, that's true with this one too. In the partially lucky mean, if x4 is really big, I got a 1/6 in front of it. So this one also depends on all of them. I see. You guys don't like that I was throwing some away. Okay, let's throw out these ones. Let's throw this one out. Let's not talk about this one. Let's not talk about this one. Let's talk about the partially lucky one, because the partially lucky one depends on all 4. And you people are saying don't throw one away. If you throw one away, that's silly. You got to use all your data. Look, I'm using all my data. It's just that I'm using x3 the most because 3 is lucky. Okay, so I'm not getting rid of any of them. Could we explain to somebody why is this worse than the ordinary mean? That's what we got to do. All right, yeah. It's biased. Okay, let's check. This is great. I claim it's unbiased, but let's do the verification. So let's call this mu hat partially lucky mean, the PLM, new acronym for this class. What's the expected value of the mu hat of the partially lucky mean? This is amazing. Okay, it's the expected value. Let's write down the formula. It's 1/6 times x1 plus x2 plus x3 plus 1/2 x3. Okay, wait. This is x4 because 3 is the lucky number. Okay, now I'm going to use linearity of expectation. So the expected value of 1/6 times something is 1/6 times the expected value of something. The 1/6 jumps out. Okay, so this is 1/6 times the expected value. And in fact, instead of doing x1 plus x2 plus x3 and then taking the expected value, I could do the expected value of them individually. x1 plus x2 plus x4. Okay, now we're cooking. Plus 1/2 times the expected value of x3. And all of these are 4 samples from the same distribution. All of these things are the true mean mu, right? So this is 1/6 times mu plus mu plus mu plus 1/2 times mu. Okay, got 3 copies of mu over here with a 6th. I got a half of mu over here. So this is 1/6 times 3 mu plus 1/2 mu. And by my math, that is mu. The average of the thing I'm estimating is mu. So it's unbiased. Yeah.
I'm thinking you are giving more weight to these 3.
Yeah, we're giving, well, okay, here's the thing, right? 3 is not, in real life, 3 is not actually lucky. So you're right, it's like we're giving more weight to 3. And like you have a good intuition, that's like not fair. Like that's like bad, right? Like why should we give more weight to 3? And I think part of the reason this is a hard answer to explain if you don't know the right way to look at it is that the partially lucky mean will sometimes be better than the regular one, right? It's not that it's always worse. And so like in particular, if x3 happens to be closer to the mean than the other ones, then the partially lucky mean will actually be better. Like if in an actual real life data set, the partially lucky mean could be better than the regular mean. So it's not that it's always worse, right? It's just that it's like on a macro level, if we repeat the experiment many, many times, then we should expect it to be worse, right? So this is the like fundamental issue. And this is what we have to understand when we're saying something is better than something else. Like when we're going to talk about the biased estimators in a minute, we're going to have to understand what does it mean to be better at all? And then why is this one worse than the other one? Let me open a little mathematize here, which is how do we measure which is better in the first place, right? This is the kind of question. This is like fundamentally, we need a way to measure which one is better. Like we need some calculation you do that tells you this one is better than that one. How do you measure? Okay, I'll let you think. I think you know the answer to this. If you think about it, if you phrase the question this way, I think you will all know the answer. Okay. Put in your final guesses. The answer might be, I don't remember. That would be fine. How do we measure it? Which is better? And people said, ha. Okay, great. I like this. In giant letters, variance. That's a good start. MSE, also quite big. And that is what I would say. The MSE, great one-word answer. Yeah, so unfortunately, this is the problem. Biased does not tell you which is better, right? We have two unbiased ones. They're both unbiased. One of them is definitely better than the other. So biased and versus not biased is actually not the distinction of better versus worse. And that's what we need. We need something else. So someone wrote with the variance, probably a few people wrote about variance. It turns out variance on its own is not what we want. Variance is part of the equation. We're going to see that in a minute, but it's not only the variance. The one that is more accurate most of the time. This is another common misconception, right? If we were doing classification, if we said we want to get the class exactly right, then the accuracy is how often you got it right. But when we're trying to estimate a number, you will never get it exactly right. So you need some kind of notion of how close you were, right? And so accurate, usually in data science means getting it exactly right in classification. We don't want to be accurate. We want to be as close as possible. If you use the street version of accurate, I guess that's what the street accurate means. So we have to say exactly what do we mean by accurate, and we have a specific thing. We have error. Yes, the one with lesser error. That is the right kind of thing. How are we going to measure the error? So yeah, this person is telling me things that would be good. It would be nice if we had low bias and low variance, but like how do we combine these things? And there should be the mean squared error. Beautiful. This is a great answer. Comparing the mean squared error. Let's do the mean squared error of these things and see which is better. And so this is the key thing. When we are talking about better or worse, we are often talking about lower average error. Better, worse. When we say things like this, what we actually mean is means lower, higher, lower average error. Lower, higher, I guess. Okay, lower, higher average error. Okay, and okay, again, on the street, accuracy and error kind of mean the same thing, right? If you have very low error, you have very high accuracy, but be careful because accuracy in data science or statistics means how often you got the class right, and we're talking about the distance. And in particular, here we're using the mean squared error. In particular, we often use the mean squared error, which is the mean of the square. So we're doing the expected value of how much mu minus mu hat squared is. That's what we want to do. We're going to calculate this thing for our two estimators, and we could do this for the mean, and we could do it for the partially lucky mean, and we can see which one is better or worse. Mu minus mu hat, the partially lucky, did I make this PLM? All right, the partially lucky mean. And we could calculate, and this is like, on average, this is 0, but how far away are you, right? This is the thing that matters. And we're going to see that for the mean, it's lower than for the partially lucky mean. So this is the explanation of why the partially lucky mean is worse. The partially lucky mean, even though it's unbiased, has a worse mean squared error. Worse mean squared error. And we're going to see why exactly. So to calculate this, again, we're going to use the Pythagoras formula, which we did in the first week, the Pythagoras formula for random variables. And both things, let's draw a dotted line down the middle. The average error for the regular mean and the average error for the partially lucky mean, they will both be a sum of squares of things. So this one will be, let's write it out like this. It's going to be 1/6 squared times the average value. Let me just skip some steps, and I'm going to write out what it is. It's the variance of x1 plus 1/6 squared times the variance of x2 plus 1/6 squared times the variance of x4 plus 1/2 squared times the variance of x3. So remember, the partially lucky mean was a 6 times x1, a 6 times x2, a 6 times x4, plus a half times x3. When you do how big it is on average, you're going to get the variance of them getting added up with a 6 squared, a 6 squared, a 6 squared, and a half squared. That's the Pythagoras formula. They add up with the squares. For the ordinary mean, it is a quarter squared times the variance of x1 plus a quarter squared times the variance of x2 plus a quarter squared times the variance of x3 plus a quarter squared times the variance of x4. Okay. And this one's very nice. You have a quarter squared copied 4 times. All of the variances are equal. Normally we call this thing like sigma squared. The variance of x I equals sigma squared is some constant. In this example, I'm just going to pretend it's 1. And that was what was being done in the Python code as well. It was just 1. And so this whole thing equals 4 times 1 quarter squared, which is also known as a quarter. So the ordinary mean has a mean squared error of a quarter. On average, it's a quarter. And actually, we did this. I don't know if you remember in the code, the mean squared error was a quarter. Where's the code at? Here it is. We repeated it 10,000 times, and the average mean squared error was 0.249. That's very close to the true average error, which is 0.25. So this is kind of all working out the way we think it is. Let's do the partially lucky one, and let's calculate what it would be. I guess it would be 3 times 1 over 6 squared plus a quarter. So 3 over 36 plus a quarter, that's a 12th plus a quarter. Hey, wait a second. Why don't I leave it as a 12th plus a quarter? Because look, you can see it's already bigger than this one, right? This one was a quarter. This one is a quarter plus a 12th, right? So this is fundamentally the reason when you do the sum of the squares, you want to spread them out as much as possible, right? You want to have the minimum variance, and the variance goes by the square. So you want to make the numbers, you spread them out as much as possible, so that way when you square them, they get extra small. If you do something silly, like put a bigger weight on one of the numbers, you're going to pick up more variance. And that is why the partially lucky mean is bad. And this is like the intuition of we want to spread out the error as much as possible, right? Spread out dependence. Out the dependence. Dependence. And so equally spreading it out, the mean of all the ones that are like linear combinations of all the observations, the mean spreads it out the most. The mean is the one with the smallest variance of this kind of silly thing. Anytime you write numbers like this, the mean is going to be it because it spreads it out as much as possible. Okay, so we have a good answer there. These were both unbiased. In general, what is true in general? This is the thing that we want to get to. In general, we can always decompose as a bias variance trade-off. Okay, and basically all of this, what we've done so far is a warm-up to remind us of this formula. That the thing we care about is the expected value of mu minus mu hat squared. That's the error that we were just doing. And it can be written in 2 parts. There's the variance of the estimator. The variance of the estimator. Let me write down the bias first, actually. So there's the bias, which is the expected value of mu hat minus mu. So if this is 0, it's unbiased. If this is not 0, if it's positive or negative, then it would be biased. You square that. This is the bias squared. So the total error, the mean squared error, is written as the bias squared plus the variance. And the variance is exactly the thing we just calculated. In the example we just did, the bias was 0 for both things, and so the mean squared error was only the variance. But in general, you have some variance. Should I write out some funny variance thing? Yeah, all right, fine. Let's write the variance, and it's the variance of mu hat minus the expected value of mu hat. So whatever the thing is, I'm just gonna write this as the variance, like that, plus the variance. Okay, so amongst things that are unbiased, you would like to make the variance as small as possible. If you make the variance as small as possible, then the mean squared error will be as small as possible. If the bias is 0, then this is the only term. Okay, very good. Questions or comments so far? We're about to start doing some unbiased things. It took us a while to get here, but all right. Let's be unbiased. So how on earth, how is it possible that biased is better, or biased could be better? Biased could be better than unbiased. Okay, I just told you the mean squared error is bias squared plus the variance. If you make this bigger, you increase the bias squared. What the hell? You're just making the mean squared error bigger, right? So I want to make this, I'm like, hey, look at this nice term you have over here. Let's make that even bigger. How on earth could this be good? The secret is you have to be biased in a particular way. You have to be biased in a way that increases your bias term but decreases the variance. So this is the only way. So this term must go down, otherwise you're doing something very silly. How is it possible that the bias could be better? Answer, works, let's say, if it decreases the variance, it could be better. If it decreases the variance, then it could be better. It could be better. Okay. Right? Here's a very simple way you can make this term 0. This term I wrote in green, you could make it 0. Example. Here's an estimator with 0 variance. Estimator with 0 variance. Also, this one is going to be biased. It's a biased estimator. A biased estimator with 0 variance. We can make this term so small. Here's my estimator. You ready? Mu hat. Remember, it's a function of the things. It's the estimator of x1, x2, x3, x4. We input our 4 numbers. We're going to output a number, and I want it to have 0 variance. I want it to not vary. It's going to be really solid, stable estimator. Does anybody know what I'm going to write on the board? Next, an estimator with 0 variance. You thought the dumb mean was dumb. This is even dumber. An estimator with 0 variance. Well, whatever I write better not change. It better, because if it changes, right? If it's going up and down, then it would have some variance. Just like these ones, right? These ones have some variance, right? Like this 1/6 x1, x2, x4 plus a half x3. As x1 and x2, they vary, they go up and down. This whole estimator will go up and down. And that was where the variance of this partially lucky estimator came from. So I want 0 variance, no variance at all. So what could I possibly write down over here that has 0 variance? Yeah. 0. Yes, 0. You give me the numbers x1, x2, x3, x4. What do I think the mean is? I think it's 0. All right, you gave me the number 7, 14, 5, 3, 0. You give me the number 1 million, 2 million, 3 million, 4 million, 0. So this is like even dumber than before. This has no variance at all. No variance at all. However, did I make it better? No, I increased the bias squared. This thing is super biased. And I increased the bias by a lot, and I decreased the variance by a lot, but I did it in a dumb way, and the total mean squared error is going to be worse. This guy over here, this will have 0 variance, but huge bias. Okay, and so overall, this is a really stupid estimator and is not going to do well. It's going to have really bad error, even though it has 0 variance. And this is the trick. This is the whole art of this unbiased thing, is you cannot go too far. You have to balance. We can make the bias squared a little tiny bit worse. If we make the variance a little tiny bit better, but if you go too far, then overall it's gonna get worse. So this is the trick. You just have to do a small change to make the variance smaller at the cost of making the bias squared just a little tiny bit bigger. If you go too far, it will not work. So the could here, the could is doing a lot of heavy lifting. You gotta make sure you don't go too far. And the simplest example you saw, this is the first thing that I'm gonna write down in this class that is kind of a non-dumb estimator, a real, honest to goodness, smart, super genius thing, which is called the James Stein estimator. And hopefully you watched the video and you know a little bit about it. Estimator. And I'm going to summarize it like this. So James Stein, I'll call it JS for short. JS of x1, x2, x3, x4. It's going to take the variables and it's going to calculate the honest mean. So it's going to do the honest mean of x1, x2, x3, x4. And then it's going to do something I think which seems very counterintuitive, but is actually like genius. It's going to multiply the mean by a number that is a little tiny bit less than 1. I'm going to call that lambda JS. And it turns out lambda JS actually also depends on x1, x2, x3, x4. And this is the whole point is this is just a tiny bit less than 1. Tiny bit less than 1. Okay. And this is the secret. It can't be too much less than 1. If this was 0, we would be back into this guy that always outputs 0. So if it was a lot less than 1, this would be very silly. But if it's a little tiny bit less than 1, this is actually genius. And I'm going to calculate, before I even run it, I'm going to show you the mean squared error of this guy. So the mean squared error of the JS, it's the bias times the variance. By making this, if this was exactly 1, it would have no bias. But it has a little bit of bias because this is a little bit less than 1. So let me not write equals. Let me just say like vibes. This is approximately. So it's lambda JS times mu minus mu all squared, right? This is the true mean. This is the mean of the JS, right? So if you multiply by some number, then that multiplies over here. And okay, this is actually a lie because this is a random number. It depends on x1, x4, but like, very roughly speaking. And so if this was 1, then these would perfectly cancel out. Because it's a little bit less than 1, you're going to pick up an error term, right? So this equals mu squared times 1 minus lambda JS squared. So you have some bias. The bias before could have been 0, but now we're increasing the bias by whatever 1 minus this lambda is. But, so this went up. The bias went up. And the only reason this could be worth it is if the variance goes down. And fortunately, it does. What is the variance? Well, the variance, remember, goes by the square. So when you multiply the whole thing by lambda JS, the variance goes by the square. Okay. And then you multiply all this by the variance of the mean, roughly. Let's say mean. So let me write down the final thing. Plus lambda JS squared times the variance of the mean. Let me just write variance. We're being sort of imprecise anyway. Variance. Okay. So the bias went up, but the variance went down. Variance went down. Let me say the variance here, I mean the old variance. Whatever the variance was before, it got multiplied by lambda squared. So the bias, if this is a number that's a little bit less than 1, this is some non-zero number, it went up. But the variance, if this is a little bit less than 1, it went down. And the whole thing, the whole reason this works is that these James Stein people, they came up with this like really genius way to make sure how to find the right value that makes this go down, lambda JS, such that the overall mean squared error went down. And that is what they did. So they have this really famous paper. How to find? Well, they did it. James and Stein did it. James and Stein did it. Okay, and we won't just go into the super details. It depends on a number of things. But this is the idea. We shrink the whole thing a little bit, and by shrinking the whole thing a little bit, we shrink the variance at the cost of some bias. But if you do it just right, you will get a favorable trade-off, and you will actually get less overall error. And if you saw that video, it's a very popular video on YouTube. It has over 1 million views. They kind of explained some pictures of why this works. Let me show some of the pictures from the video. There's some nice geometry. Okay, let's show the geometry. So there's some picture like this, where this is the true thing you're trying to estimate, and you arrange the shrinking so that you shrink more in this region and shrink less in the other regions. If you haven't seen it, you should absolutely watch it. It's a very good thing on the pre-class playlist. But let's see it in action in our Python code. So this was the unshrunk estimator, right? It was getting it exactly right on average. And the James Stein estimator, there's some formula for this lambda JS, and the whole point is that it's a little bit, tiny bit less than 1. It's 1 minus a tiny bit. And then I ran it exactly on the data we had before, and this is what came out. So the James-Stein factor in the setup that we had before, on average, was 0.92. So instead of being 1, which would be completely unbiased, it's 92%. So it's a little bit biased. It's shrinking everything just a little bit. And the mean squared error is now 0.23. So before, the mean squared error, I will remind you, of the ordinary estimator was 0.25. So this is an example of figuring out you can do this shrinkage so that on average you do a little bit better, and now you are biased. In what way are you biased? Well, you multiplied everything by 0.92 basically. So here is the variable 0. And before, remember it was nicely spread around 3. We've multiplied it by 0.92, so we've shrunken it. When you shrink numbers that are close to 3, they get closer to 0. So it's all a little bit to the left. So this is with the James-Stein, and this is without the James-Stein, right? This was unbiased, and this is biased. So this looks worse, but remember, the whole point is that on average we have less error. Okay, what about variable number 1? Hey, this doesn't look bad. What's going on here? So that's what it looks like with the James-Stein. Oh, it's pretty good. What did it look like before the James-Stein? It looked like this. Hey, no, this one. Okay. Hey, that doesn't look too bad. That doesn't look like it shrunk at all. Wait a second. I said that it shrunk. Why doesn't it look like? Why does this one look like it didn't shrink? What's going on? I said I multiplied it by 0.92. It's supposed to shrink, right? It's supposed to like this one shrunk. This whole thing is shrinkage. We took the thing, we shrunk it. This one, variable 1, I shrunk it and nothing happened. Oops, did I make a mistake? What's going on? Why didn't it move? This one still looks unbiased. Okay, wait. You're comparing variable 1 to variable 0. You're saying this was 4.5, and then over here, it was 1.5. Okay, yes. You should think of these as like two separate variables, right? So this one, the average was like this before. Let's put them next to each other. It was like this before, 1.5 to 4.5. With that, the true average was 3, and our data was always around 3. Sometimes a little bit higher, a little bit lower. And then we did this whole James-Stein thing. We multiplied it by a constant, and it became like this. So it shrunk. But then in variable 1, the other variable, a different variable, it used to look like this. So it was unbiased. The line is in the middle of all the data. That's unbiased. And then we shrunk it, and it's still unbiased. How come variable 0 got shrunk, but variable 1 didn't get shrunk? I'll tell you, there's no bug in the code. There's a very simple explanation. Yeah?
Because it's 0?
Because it's 0, exactly, yeah. So what does shrinking mean? Shrinking doesn't mean go to the left. Shrinking means get closer to 0, right? So you see, this is the thing. We're literally multiplying. If we go to this, I think this is an important thing to understand. We are literally taking whatever the answer was and multiplying it by a number, right? So this is what shrinking means. Multiply it by a number that's smaller than 1. That does not mean make it smaller. That means make it closer to 0. If it was a negative number, it actually goes up. Whatever the numbers are, they get shrunk. So they get shrunk. Shrunk means get closer to 0. So for this one, where they were positive numbers, they were starting at 1 all the way up to 4.5. When you multiply it by 0.92, then you shrink the numbers, it moves to the left. But if there are numbers that are sometimes negative and sometimes positive, when they're positive, you make it smaller. When they're negative, you actually make it bigger, right? You multiply it by 0.92. Negative 1.5 times 0.92 is like negative 1, so it actually moves that way. And so you don't see any movement on this one. This one is actually still unbiased. The mean was 0 before. You took the mean, you multiplied it by 0.92. 0.92 times 0 is still a 0. So this one is still unbiased. I will say, though, this one is a great example of why this thing works, right? Look at it before and look at it after. There's a very subtle difference. Here is it before, and you'll notice the graph goes from -2 to +2, and like -1.5 and 1.5 are the absolute edges of the sample we have. After we shrunk it, it got smaller. So this graph only goes from -1.5 to -2 to 1.5, and it's a little bit smaller. if it has less variation, it's going to contribute less to this variance term. So seeing that this distribution is more tightly centered around 0 because of the shrinkage is exactly why we're picking up this term over here. We're making this term, it really, when it's mean 0, you really see that kind of happening explicitly. Okay, that's very nice. What do you think is going to happen? This is a good test for your understanding if you're paying attention. The variable 0, variable 1, and variable 2. Variable 2 is at -4 before. Where is it going to be after the James Stein? So before, unbiased, just this passive mean, -4. What is it going to do? Let's see what it looks like. And let me see if I can bring it. There's variable 2. This one moved that way. And that's because we multiplied it by 0.92. It got less negative. It got closer to 0. And so the whole thing shifted to the right. So the James Stein estimator shifts things in a particular way. It makes them closer to 0. And when you make things closer to 0, they have less variance, and you get less overall error. So that is the moral of the story. The whole point is to understand this, is this idea that you can get some advantage by increasing your bias as long as it decreases your variance. And it's really important that you decrease your variance. If you make bias and also make variance, then this will not work. And it's very important that you do it in a balanced way. You don't do too much or too little. Okay. Any questions or comments so far? This James Stein thing, I think, is very counterintuitive. If aliens told me there is no such thing as the James Stein, I'd be like, yeah, that makes sense. But there is. I don't know. We live in a weird universe. Okay, let's move on to the next little topic here. Here's the thing about the James Stein estimator. It only works for this particular Gaussian setup. Everything has to be exactly Gaussian and exactly nicely set up. If they were arbitrary distributions, so it was like way back at the beginning, I think I wrote, here. The James Stein is a proof that works in this situation where things are normal according to some mean. What if they're not normal? Could this still work? Does it still work? So question. Does shrinking by lambda work? Let's say by a factor of lambda work if the data is more ugly? Could it still work? So, in other words, James and Stein, they came up with a formula, and it's a beautiful formula, and it depends on the data in a very particular way. But what if you don't have that formula? Can you make this kind of thing work? And I think I have a mathematize for this one to get your opinion on what we're going to have to do to make this work. Okay, let me close this. So we're moving away from the James Stein, and I want okay. Yes. Okay. Here's my specific question that I will ask you. That is trying to get at this question in a way we can possibly answer it. So here it is. So instead of using the James Stein shrinkage factor, which is some funny function lambda, forget about what it is. So James and Stein came up with this crazy formula. What if we just always multiply it by 0.9, by a constant shrinkage factor? So an example is 0.9. Could it still work? So instead of saying let's do a crazy function, let's just we'll go into this thing, and we're going to do the example. New example. And I'm just going to fix lambda. Fix lambda, and so it does not depend on the data. Does not depend on data. Here, and then I just do the new estimator. Should I give it a provocative name? Let's call it the silly estimator. The silly could be good, silly could be bad. You don't know. The silly estimator. Estimator of x1, x2, x3, x4, and it's lambda times the mean of x1, x2, x3, x4. So in other words, I have removed the genius of James and Stein, who had that crazy formula and the proof that it always works, and we saw that it worked, and I have replaced it instead with a fixed lambda. So just some number. Could that still work? And I want your opinion just on the mathematize. Of course, you have no way to know for sure, but do you think it can still work? or no, that won't work. Those are your choices. I'll let you think for a minute about what you think is going on here and how the mechanics of this thing work. Do you think this has a chance of working? Okay. Okay, 5 seconds left. Could it work? Could it not work? We're going to find out. Okay. 19 people said yes, it can still work. Good optimism about reality. Sometimes optimism about reality is warranted and sometimes it's not. What universe are we in? Let's find out. And I want this one. Okay. So let's try it with a constant, and I think that's the next little section. Fixed shrinking factor. For any fixed lambda, we can just shrink the mean. Lambda times the mean. Okay, great. That's my silly estimator. And here I've tried a few of them. So mean squared error on the y-axis versus the shrinkage factor. And look at this. So 0, wait a second. Lambda is 0? The this is the shrink factor 1 minus lambda. Okay, let's see what's going on. Let me try to get this correct. Mu hat times shrink factors, and then shrink factors from 0 to 1. Okay, great. Yes, this makes perfect sense. Okay, great. I'm with it now. So the shrink factor, this is what I call lambda. Lambda equals 1 is the ordinary mean, right? You multiply the mean by 1. Lambda equals 0, this guy over here, we've actually seen earlier in the lecture. Lambda equals 0 is the world's dumbest thing of always estimate 0. This one, the biased estimator. The estimator equals 0. 0 times anything is 0. So we've seen this one before. And so if you look at this graph, you might conclude, yeah, this doesn't work, right? Like, this is the worst. This is a little bit better, this is a little bit better, and then like lambda equals 1 is the best possible thing. So what are we doing over here? But if you look more closely, if you really zoom in, can I really zoom in? Will the computer let me zoom in? Let's zoom in. Oh God, this is let me scroll down. Okay, we gotta zoom in. Look at this. Look at this. It is mostly going down, but then it goes up just a little bit right at the end. Okay, so let's try to zoom in a non-dumb way. Look here. Here's the same plot, but plotting everything from 0.8, starting at 0.8 and ending at 1. So 1 is the ordinary thing. 0.8 is a shrink factor of 80%. And 0.92, remember we did 0.92, that was the James Stein. If you do around 0.92, then it does get a little bit better. So what is the moral of the story? If you shrink by a little tiny bit, and the amount is not too much, and it's pretty close to 1, then you can improve your mean squared error. The mean squared error goes from 0.25, a quarter, to like 0.23. This might seem like a whole, a mess of an improvement. Like, are we improving by a lot? But this is like a 10% or 20% improvement. So this is actually can be quite significant depending on the application. So this is the moral of the story. If you shrink things, you can trade off variance for bias in a way that is favorable to you and improve the estimator a little bit. There is one problem. Here is the problem. I will also open this in Mathematize for you. In real life, you cannot make the graph I just made. You cannot calculate the true mean squared error. The graph I made, I knew the right answer. I knew the actual secret mean, and I was using that to calculate the mean squared error. However, you can estimate the mean squared error for different values of shrinkage by using what? How would you do this? Okay. again, if you've been paying attention in the course, this should be kind of the bread and butter topic that we've done so far. Okay, let's see. How do you estimate the mean squared error? Should be old hat by now. This time people said, drum roll, validation. That's it, right. You make a validation set. You do your train test split or training and validation split or cross validation is the other way. So yeah, you instead of getting it exactly, you get it approximately by just using a held out set. Let's see, where is it? I think that's the next thing. Okay, here's the shrinkage that we did. Okay, I didn't even do it because yeah, it's we've done this a bunch of times now. So what is the moral of the story? This shrinkage factor is very similar to a lot of the other methods we've done in the course. In real life, what you will do is you will do a training test split. So in real life, what is the application to real life? In real life, use validation to compute the optimal amount of shrinkage. Compute the optimal amount of shrinkage. And so this is the moral of the story, is you can improve your models by shrinking it towards zero. Shrinking it towards zero can improve it because it decreases the variance, like we saw over here. You have to be careful because decreasing the variance, although that's good, increasing the bias can be bad, and you got to make sure to balance these two things. And in real life, you have to be careful how to do it. So use validation to compute the optimal amount of shrinkage. The other big improvement, and that we will talk about on Wednesday's class and on Monday's class, is so far we have shrunk everything equally. So far, everything is shrunk equally. In other words, there was one value of lambda, and we were applying lambda to every single mean. We were shrinking everything by the same amount. But there is a lot to be gained by doing unequal shrinking. But in real life, it is better to shrink unequally. To shrink some more and some less. Some more and some less. Okay. And we will go into this on Wednesday's class. Let me give you a quick little preview of the kind of thing we're going to do on Wednesday's class. Where is the thing I want? This one. And I will open it for you. This is something we saw a few classes ago where I had a data set where I was trying to tell you don't decide on variables just based on correlation. And the reason was you had, for some data set, maybe one predictor is the best. And for another data set, four predictors are the best. So depending on, you have the same data, more or less variables might be useful depending on what's going on, depending on the y values. So you cannot just look at the x values to decide. And we're going to see next time that if you use something called ridge regression, this will shrink the variables unequally. So you'll get these plots of how much things are shrinking, and you'll see that some of them shrink a lot and some of them shrink not much. Versus for the other one, it'll look a little bit different. This is what was this y1? So we're going to go into this next time, and this idea of unequal shrinking. This will lead us into ridge regression, ridge, aka L2 penalties regression, L2 regularized, let's say regularized and lasso, which will be aka L1. And we're going to see those on the next two classes. Okay, I think that is a great place to end the lecture. Any questions or comments? All right, let's stop there. We'll see everybody on Wednesday. Make sure you start working on your project twos, which are due. The draft is due sometime soon-ish. I will post a form where you can report who your partner is, or if you haven't found one yet. That will be going up probably today. Okay, see everybody on Wednesday.